Hi everyone, Professor Bob Young. This is video 6 in the college trigonometry series. In our last video, we discussed graphing sine and cosine functions along with their variations. In this video, we're going to discuss their reciprocal identities, the graphs of the cosecant and secant functions along with their variations. All right, so the graphs of y equal cosecant x and y equal secant x are obtained from graphing their reciprocals, as I mentioned. So the cosecant x, if you can graph sine, you can graph cosecant. If you can graph cosine, you can graph secant. Now the difference here is the vertical asymptotes of y equal cosecant x occur at the x-intercepts of y equals sine x. So in other words, when the sine is 0, the cosecant is undefined because you can't have 0 in the denominator of any fraction. And similarly, with the cosine, vertical asymptotes of y equals secant x occur at the x-intercepts of y equals cosine x. So when the cosine is 0, the secant is undefined. So we're going to look at some characteristics first of y equals cosecant x. Now notice here we have the graph of y equals sine x right here. And I went ahead and made a chart up here and I let x be 0. So when the sine is 0, we're at 0, all right? But there is an asymptote here, the cosecant would be undefined. Now you can't see the asymptote good when it's the y-axis, but you can see the other asymptotes and so forth. Notice when the sine is equal to pi, the sine of pi is 0, the cosecant is undefined. So this draws another vertical asymptote, or as I'd like to say in my other videos, the va. That's what I nickname vertical asymptotes. All right, so as we go along here, the sine of pi over 6 is 1/2 here, so there's that value. Notice its reciprocal, the cosecant, is up here at 2. All right, at pi over 4, we're at 0.7, about halfway here, 1.4. At pi over 3, we're getting closer to pi over 2, we're at 0.87 or 1.15. And notice at pi over 2, they both are 1 because the sine of pi over 2 is 1 and the reciprocal of 1 is 1, so you're there. And also I threw something else in here. I threw some values pi over 10. I got closer and closer to 0 here. Pi over 100, pi over 1,000, and so forth. And as you can see, if you take the sine of pi over 10, I put approximations here, of course, on these three. The sine of pi over 100, the sine of pi over 1,000, you're getting closer and closer and closer to 0. And as that happens, notice that the cosecant grows infinitely larger and it will go to positive infinity. So if you think about the sine of pi over 1,000,000,000,000, for example, this number would be astronomical heading to infinity here. All right, so the domain of the cosecant, because of the asymptotes, is all real numbers except integral multiples of pi. Okay, so notice every interval of pi you have an asymptote here. The range is all real numbers y, such that y is less than -1, less than or equal to -1, or greater than or equal to 1. And here it is in interval notation. So this goes from 1 to infinity, -1 to infinity, and this will keep happening forever and ever. All right, more characteristics of cosecant here. We said the vertical asymptotes are integral multiples of pi. Notice this is an odd function. If you were to take the cosecant and put a minus x in there, it will change sign, therefore having origin symmetry or being an odd function, as we have said. Notice this thing revolves the cosecant about the origin. Now, as we discuss y equals secant x, the reciprocal of cosine, we can have a similar argument here. Notice that on the secant, you have the domain is all real numbers except odd multiples of pi over 2, because remember, the cosine of pi over 2 is 0. All right, so that draws an asymptote on its reciprocal, the secant. So instead of multiples of pi like like sine and cosecant, the secant has odd multiples of pi over 2 because that's where the cosine is 0 and makes the secant undefined here. And again, range all numbers between, well, not between, outside of -1 going -1 to negative infinity heading down and 1 to infinity heading up. So characteristics very similar. The only thing difference is where the cosine is 0 versus the sine is 0 to establish these graphs. So we mentioned the vertical asymptotes, odd multiples of pi over 2. Now a lot of places will put pi over 2n here, you know, as n being an integer, 1, 2, 3, 4, forever. And notice this is an even function. So when you take and replace secant with a minus x, you get that same thing back, has y-axis symmetry. And you can notice this is splitting, y is splitting this in half here. And notice over here to here is equally distanced from y, symmetrical about y, as is over here and over here. You can see that y symmetry indeed. All right, so let's go ahead and graph a few of these creatures here now. And we're going to start with y equals the cosecant of x plus pi over 4. Now we're going to use the graph of y equals the sine of x plus pi over 4. It's reciprocal to do this, so let's just act like we're graphing sine from the last video. We said the amplitude, the number in front here, absolute value of 1 is 1. The period 2 pi over b, now the b number here is 1, so we'll get a period of 2 pi. The phase shift here, you've got the c number. Now if you're thinking about this, x plus pi over 4, you might be thinking, well, this thing, is it going to go right or left? This one I think would shift left pi over 4 units. So it would be pi over 4 over 1. So if you want to, we can put the minus there and say that would be a minus pi over 4 shift, or a pi over 4 shift to the left here. All right, so now we know that the phase shift, we would begin at negative pi over 4, and then to get those nice x values, we would take that period of 2 pi and divide it by 4 for pi over 2 increments. So we would keep adding pi over 2 to this value all the way down to get our 5 nice values. So negative pi over 4 plus pi over 2 would be pi over 4. Another pi over 2 would be 3 pi over 4. Another pi over 2, 5 pi over 4. And another pi over 2 would be 7 pi over 4. And don't worry, we're going to cheat on the sine graph like we tend to do. All right, so if you take the sine and you put negative pi over 4 in here, you're going to get the sine of 0 is 0. At pi over 4, that's going to give us a sine of pi over 2 is 1. So I'm going to go over here, negative pi over 4, 0. I'm going to go pi over 4, 1, and I think y'all are going to start doing the me. At 3 pi over 4, back to 0. So you've got intercept, maximum, intercept, minimum, intercept over here at 7 pi over 4. And if you want to, we can keep going here. So I'm just going to go ahead and do this with just a little dotted line here, because we're really graphing the cosecant now. We're not graphing the sine anymore here. We have to get the sine to see it though. And if you want to, we can keep going pi over 4 in the other direction here as well. So if you want to, we'll go ahead and say intercept, minimum, intercept, maximum. So we can just get a nice graph out of this here. So here's what our sine graph would look like. All right, so to graph the cosecant now, wherever the sine is 0, in this case, wherever y equals the sine of x plus pi over 4 is 0, this is going to be undefined, the secant, because you can't have 0 in the denominator. So we can go ahead and shoot some asymptotes here. So wherever sine is 0 or an x-intercept, I'm going to go ahead and put some asymptotes. And in class, I'll sit there and I'll go da, 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 da. when I do this, so just to be kind of corny. I can be corny on the videos too. I can make these higher and go way up there, but I don't need to. All right, and I'm going to go ahead and choose blue to show you y equals cosecant of x plus pi over 4. I like to use plenty of colors here. So again, where the sine is 1, the cosecant is 1, and what happens is as this gets closer and closer to 0, the reciprocal goes off like we discussed earlier to infinity, and try to hug those asymptotes. Again, with my writing tablet here, this is a very smooth surface I'm graphing on here. It doesn't always do exactly what I want it to do, but I think you get the gist here. And then I like to call this the peak and the valleys here. If that's -1, its reciprocal's -1 there. And again, as this gets closer and closer and closer to some small negative value here, that gets larger and larger going the negative direction that way. And again, wherever we have those peaks and valleys, we'll go ahead and graph the reciprocal functions. And you can even come over here if you want to, and you can do this as many periods as you want and so forth. So there is the graph of a cosecant function. All right, for our last example here, we're just going to do an example of a secant graph for you. And again, if you can graph sine and cosine, you can easily graph secant and cosecant. So we're going to use y equals 2 cosine 2x to graph its reciprocal identity cousin here. So using our graph here, running through the steps again, the amplitude would be 2. The period would be 2 pi over b, which the b number here is 2. So that would give us a period of pi for this cosine graph. There is no c number on this one, so 0 on the phase shift. And the nice x values would be the period divided by 4, so that would be pi over 4 increments. So if we started with 0, since there is no phase shift here for the first x value, before we plug it in up here, and keep adding pi over 4 to this all the way down to get our 5 nice values. 0 plus pi over 4 is pi over 4. That next one would be 2 pi over 4, which would reduce to pi over 2. The next one would be 3 pi over 4, and then we would get to pi here. So plugging in the cosine, if we went ahead over here and said 2 times the cosine of 2 times 0 is 0. The cosine of 0 radians is 1 times 2 is 2. And again, you can use your calculator and radian modes to check this. Pi over 4 here would give us 2 times the cosine of 2 times pi over 4 is pi over 2, which would go back to 0. At pi over 2, we would get the cosine of pi -1. And then I think y'all see we can start doing our cheating ways here. So 0, 2, pi over 4 is halfway between pi over 2 and 0. So pi over 4, 0. Pi over 2, -2. 3 pi over 4, I think, would go back to 0. So me, maximum, intercept, minimum, intercept, maximum, intercept, minimum. We can keep doing this. Maximum, intercept, minimum, intercept. And we can keep doing this forever and ever. So we'll go ahead and, oops, I want to get down there a little more on that one. And we'll make a real light cosine graph here. And again, my writing tablet is slip and slide. I'm trying to make these curves as nice as I can here. I don't want to make tips on the iceberg. I want to make these. Okay. So now, where would our asymptotes be out there, ladies and gentlemen, if we were going to graph this? And we can go up just a little bit more over here as well. Try to make this look a little even. So I'm going to get the red out. So wherever this cosine graph is 0 here, we're going to have some asymptotes. Okay, so wherever the cosine is 0, the secant is undefined. So we're going to have these, it looks like here, about pi over 2 intervals. I'm sorry, my graphs are not prettier, but these should work out fine. And I think you're getting the note here. If you can graph sine and cosine, you can graph secant and cosecant. All right, so in blue here, when the cosine part of this is 2, we're going to go ahead and do the peaks and valleys here. This would be what the secant looks like as well. So just stay between these asymptotes. We looked at the strategy of why this happens when we were looking at characteristics of sines and cosine graphs and so forth. And you can again make as many periods as you want. So this concludes video number 6, graphing secants and cosecants by using sines and cosines.